we are very happy to today to have a unusual kind of conference because it's not us who have invited speakers, but they themselves proposed to come. And so because the topic is so important, that means how we can anticipate the development of the cooling requirement in buildings in our country, it made really sense to accept these proposals for to hear your contribution. This summer we have all experienced what does it mean to have kind of long overheat periods. At the same time, there is a kind of energy crisis starting now for several reasons. And if we don't anticipate the fact that overheating periods will certainly amplify during the coming decades, and we just rely on technical solutions, then we are certainly going in the wrong direction. So it's the right time now to start to think a little bit more seriously, and I think everybody now is much more aware than a few months ago, I would say. Okay, so I will first give the mic to Philippe de Rougemont from the ONG NOE 21.
Yeah. Thank you, Raphaël. So my name is Philippe de Rougemont. I come from Geneva, and I am active in an NGO called NOE 21, NOE, and it stands for New Economic Orientation for the 21st Century. So 10 years ago from now, in 2012, this small NGO, we noticed that India has a very, very big building boom. In every large every large Indian city, there is a huge building boom still going on today. You see cranes everywhere. And this is happening at the same time when we know that there is a climate catastrophe, perhaps in front of us, and it's much avoidable. And Switzerland has 0.01% of greenhouse gas emissions in the world. It's huge per inhabitant, per capita, but in the total, it's little. So 10 years ago, we were so stressed out, we still are, but we saw India as a huge opportunity. If we can help the persons who are working there to boost energy efficiency in the buildings now, we can avoid a huge unnecessary use of air conditioning or reduce the tonnage of air conditioning in tomorrow's buildings. Because where do we come from? We come from Europe, where the building boom, we lived it just after the Second World War. And now we have inherited a building stock that has not been conceived to save energy, because the Second World War was a big energy fiesta. When the war ended, we could always use petrol. So you just design the building and then we'll just put more coal or more petrol and we'll heat it. And that was a huge failure. And we wanted to work in India. So we traveled there. We were looking for an NGO or an engineering company, or a mix of both, like NOE 21 is. And we met several people, and then we met Vivek Gilani and the organization cBalance, Carbon Balance. And he has been working, we have been working since together. And by, the program took hold of itself and grew and grew. What they're doing basically is working so that the universities teach smart buildings adapted to the local weather conditions, using the least energy possible as a new normal, not a course exception for people who would like to do it, but the new normal, and many other things he will tell you about. So the basic thing is that the post-war construction boom created a massive failure in terms of energy, and the return cost, I mean, the return on investment when you repair a building is so long that it's just not happening. It's 1% of the building stock that is being repaired every year, and we need to go to 3%. And if we can avoid the same thing happening towards making buildings habitable in 20 or 30 years, when we'll have the climates of North Africa here in Switzerland, that would be nice. So the idea is to go now after north-south, go south-north, and here Vivek Gilani, the engineer from Mumbai, who is head of this program called Fairconditioning, Fairconditioning, to hear what he has to tell us from his experience, and we can learn and see what we can do in Switzerland to avoid making inadapted buildings that we will have to massively air condition tomorrow if we're not intelligent today. So Vivek Gilani.
Great. So yeah, in a way, I'm glad that you sense the momentous nature of this summer and how the summer has become an educational tool that neither you nor me could have ever constructed. Like, you know, this reality is better than any fiction that you can construct about the future. So we often joke that here you'll have a heat wave, but for you all the heat wave is more like, hey, I need to go shopping for my heat wave clothes, you know, like it's like a new fashion line. But in India, heat wave it's crazy, you know. So in a way, you might see this as the future speaking to you, just like when they came to India in 2012, it was like the future talking to us. Hey, you know, you all could get locked in to a very energy inefficient building stock. And here we are trying to change the trajectory now. So if you change it a little bit now, later on, you have a much lower ramp. In a way, you might say that what we're experiencing with air conditioning in India could be the future here. So in a way, it's like a time machine, you know, speaking. So it's Father Time speaking here. But yeah, I'll tell you a little bit about this program. But let's start with the name, Fairconditioning, just to bring some interaction. Why do you think this program is called Fairconditioning? Besides it just, you know, sounding cool, why would we call it Fairconditioning? What is the unfairness that it's sort of alluding to? Yeah.
Wealthy people and countries can easily buy air conditioning from the shop, but it's not be done in most countries.
Okay, so
to find something spare, not a very efficient, cool AC system, but
right. Actually, if that was true, that would still save us. But now what's happening, at least in India, is they're planning to drop the price of ACs to below mobile phones. Like you pay through EMI, you know, you pay like 10 euros a month and you have an AC. So, I mean, India is the most unsaturated air conditioning market in the world. China is already completely air conditioned. There's not a square inch that is not air conditioned in China. So India is like this big low hanging juicy fruit for Carrier, you know, and other companies. So it is unfair in terms of cost, but there's something else that air conditioning does. And the hint is that directly in terms of the phenomenon that it causes, that it accelerates the inequities, the disparities in the world. What do you think it does when you turn on an air conditioner?
I can distribute it.
Okay, right.
Yeah, the other thing it does is like it heats up the urban environments because it takes out the heat from the apartments and emits, so it destroys the neighborhood buildings' ability to cool themselves down.
Exactly. So like the home that, you know, we pay for and the one where we live is heating up the home for every species. Forget about other human beings. It's basically making the whole earth hotter, right? So that's directly unfair. For the interests of a small group, everybody's getting screwed. That's one thing. But more than that, okay, here you don't have an energy crisis, but imagine in a country where you have an energy crisis, power shortages, like power cuts are happening quite regularly. Right now, there are 2 team members in cBalance who can't come onto calls because the town they're working in has no power. So no power, no internet, can't work. It's happening now. So imagine you have peak summer, you know, May 15th. It's hot, all the ACs turn on. And usually these are big fancy buildings, the kind you see in New York now. You have these kinds of buildings, wall of ACs, you know, like literally the facade is the AC. Like, I think this is the one good thing, it doubles up as a construction material almost. Yeah. So you have the facade of ACs, and each AC is using 25 times the energy of a simple ceiling fan. And for most conditions in India, a ceiling fan is good enough. If the ACs were sort of out of the picture, we could still keep ourselves cool with a ceiling fan. But that one AC is basically robbing power from 25 homes in a way. Yeah. To cool one room, forget about one home. So one home with 4 ACs, say you have living room, a study room kind of a thing, and 2 bedrooms. That one home is taking power away from about 100 homes. And when the power cut happens, that building and its residents don't even know that there's a power cut, because they just hear a nice bleep, and then the diesel generator continues the rape of the earth. Meanwhile, there's this building surrounded by slums. All of them are in darkness, and you will see all of them leave their homes because it's so hot, and everybody's sitting around chatting. Okay, it creates a very nice, vibrant social atmosphere. But they all cannot stay in their home anymore. Yeah. So this is directly causing inequity. It's accentuating the inequities that India already has. So just wanted to know. Okay, but there is something else a little clever. You all know that air conditioners need gases, refrigerants, and the nickname for all of them is called F gases. They're fluorinated gases, all of them. So the idea was also to say, hey, we need to keep the F out of air conditioning. And the third one is, fuck air conditioning. So it was F air conditioning. So air conditioning has 3 different meanings to it. All right, so I will go into the clicker thingy. Right, so let's talk a little bit about what this program is. Is it this? Okay. So the birth of this program, when Philippe and the Nove 21 team came to India, if you went to any university, yeah, accomplished university, like say CEPT University, it's a very well-known university for building physics, and they say that, you know what, it's fine. Our students can design the most eco-friendly buildings tomorrow. All we need to do is change the policies. The government needs to wave its magic wand, and then tomorrow everything will change. And we asked them this question. First of all, CEPT is 1 out of 450, say, universities. You guys are like the exception. Tomorrow, if the law actually gets passed that every building in India has to meet a certain performance benchmark, can the students design this? And the honest answer, even they admitted, was no. So it will most likely in India, if you have a law that has no public support, we are very inventive at creating, workarounds. Yeah, and the example that we often give is the rainwater harvesting. In India, apparently every building in India has rainwater harvesting, but you need to be on dope to really see it. It doesn't really actually exist. So only people who hallucinate will see it. So you go to these big fancy buildings and they say, oh, we have rainwater harvesting, and it's like a small little pit, and that's the rainwater harvesting system. So on paper, everything is fine. And we were quite certain that if you do the same thing with this, you have a policy that says every building has to be XYZ. You don't build any capacity in the students, no capacity amongst the teachers, no capacity amongst the architects. This will just become another sham, another fraud. So we said that, no, we can't let this happen. We need to really go to the root of this issue. So we started looking at the story going backwards. We started with technical solutions. So in the beginning, in fact, our solution was, hey, this new AC, this new natural refrigerant AC is it's the silver bullet. Let's just get this new natural refrigerant AC to become the norm. And then we asked ourselves this question, but why are buildings requiring so much air conditioning? What are we doing about the root cause of the problem? Nothing. So we worked our way backwards, and we reached academia. That's the birthplace in our assessment. The birthplace of where the AC is born is actually in the mind of a certain kind of training that the student is getting, where they're shown examples of the normal architecture is a fancy building by Zaha Hadid and Rem Koolhaas and Calatrava and all of this. So the models are this kind of architecture, which doesn't really think of cooling and those kinds of things. Yeah. So they just reproduce this over and over, and we realized that that's where we need to go. So we started studying the curriculum to test our theory. This is, I'm sorry. Yes, is this the pointer? This is the pointer, sorry. So we started looking at the curriculum of all the colleges in India. We did a study, like a 3-4 month study. And we found that out of the 423 colleges, only 25% of those colleges, about 100, had the word environment in one word in the entire 5 years of their curriculum. Only in 25% of the courses did we see the word environment being mentioned. Yeah. And from those colleges, from those 100 odd colleges, 25%, only 5% of the actual time of 5 years in terms of classroom hours dealt with the environment. So basically, you might say that 5% of 25%, right, is what is being devoted. It's like 1.25% of India's architectural curriculum, you might say, is devoted to the issue of the survival of our species and a livable earth, which was an absolute scandal. So that was the case with architecture. I'm sure every architect, when they see this, they're like, hey, why are you only talking about architecture? What about other fields? It's true that just having motivated, smart architects, but an engineering field that is still, its throat is being strangled by the air conditioning companies, right? To sell more compressors, so on and so forth, that won't help. It'll just increase the conflict between the architect and the engineer. So we do need to create an engineering world which also understands that we can no longer sell tonnage of air conditioning and make that the metric that you try to maximize. So we realized that amongst the engineering colleges, so in India we use the term RAC, it's refrigeration air conditioning, yeah, RAC. We saw that out of all the sensible, thoughtful cooling things that you could be teaching, they teach only this. Well, first of all, they all teach this. We all know this: vapor, compression, refrigeration. It's the oldest idea. It's not suited anymore as the mainstream. It can still play a role, but it can't do the bulk of the work in a climate emergency. There is this thing called evaporative cooling and solar vapor absorption. Yeah, this was an old system of cooling that doesn't exist so much anymore, but they do teach it, at least theoretically. But there's a whole host of passive cooling systems, sustainable cooling systems that are just completely absent. They never study the fact that refrigerants cause a climate problem. They never study the fact that you could actually be doing radiant and structure cooling. Imagine this. They just study compressors, nothing about radiant cooling. So we realized that there's a problem here as well. Okay, so the concluding statement that we made was that in that year when we did this study last, we realized that 17,000 students are graduating from India's colleges and are of really not much use to the climate issue. They are serving an industrial purpose. They're serving the purpose of the real estate developers who frankly couldn't care less besides short-term profit. So we have a whole bunch of students who are thinking short-term, who are designing the cheapest building that costs the least right now, but costs overall the most in its lifetime. Even literally in money terms, they're building actually very expensive buildings, right? Because it costs a lot to cool them, so on and so forth. And we realized that forget about the monetary cost, but environmentally in 2030, India will need to plant 1.35 billion trees. And the reason why we say trees is, you must be wondering, this is so childish. Who would think of, sort of offsetting the emissions of air conditioning through trees? But almost every architecture professor in India still walks around with this very naive, childish notion that, oh, to have a green campus, is fair conditioning going to help us plant a lot of trees? And we're like, no. A shading device is much more useful than planting trees. Because the trees, first of all, cannot absorb the refrigerant, right? It can absorb CO2, but what you're leaking is refrigerant. So you need to avoid using of refrigerants, yeah? So we realized that this cannot be done by first putting all those emissions out there and then trying to put them back in your bag, like once the cat is out of the bag, you can't bring it in. Okay, so we came up with a program. In fact, during the train journeys in Switzerland, I remember we used to have these discussions of how are we going to do this. Yeah. So we realized that we are not people who are comfortable wearing suits and going to the national headquarters and saying, oh, we know it. We know how to do it. You change the policy, you train teachers, and believe us, it will change. We are not those kinds of, that's not our fiber. We realize that we are very good at doing what's called, and it's a good term Philippe came up with, bottom, top, bottom, which means you start with real colleges, not the #1 marquee, super hit colleges. You start with an average college. You prove the concept that you can change curriculum in a regular bread and butter college. And sometimes they, at least we found, are the most interested, they're the most thirsty for change, because nobody's been paying attention to them, right? All the global money, Indo-Swiss bilateral aid money goes to CEPT and goes to certain kinds of big universities. These small ones are always left out. We're like, hey, that's great. We'll come talk to you. We want to talk to the real colleges anyways. So we started talking to these regular colleges, and we signed agreements saying that, listen, we will give you free training. We'll build lots of incredible resources to make your teaching much more interesting. Students will start caring about what you're teaching, because till now it's been boring equations about conduction, U values, and da-da-da-da. We're going to make it much more, learning by doing. Yeah. We'll give you these teaching aids that we have been developing. We'll create a software that will help you check whether these new cooling systems are reducing air conditioning load, all of this. But in return, we need you to take a bit of a leap. So for this year, we want you to pick 2 semesters, yeah, simultaneously. And we will attempt a changed lesson plan. You don't need to tell the university you're doing something different now. Yeah, we can do what's called outside the curriculum learning. Because the curriculum is not the maximum, it's the bare minimum, actually. A lot of colleges will tell us, oh, we can't do this. The curriculum doesn't allow it. And somebody very early on told us that's a lie. A curriculum just says what you have to make sure you teach, not all that you can teach. So we decided to work with some of these colleges, and we piloted these lesson plans over 1 year. Yeah. And our basic theory of change was, you get these colleges to become your champions, your ambassadors, and then through them, you advocate to what's called the BOSS, Board of Studies. Yeah, this is the Board of Studies that governs multiple campuses in India. So the way the university system is structured is like an umbrella. So on top sits a university, yeah, which is actually a policy making space. It's not really a physical space only. That university has, say, 50 or 60 colleges that are affiliated to that. So you change that one university, the curriculum, it causes 60 of them to now figure out how they're going to teach this new curriculum. Yeah. So the only way to get to them, instead of going horizontally to 50, is work with 3 or 4 to create a proper evidence base, advocate to the Board of Studies, hopefully with very sort of civil means of, doing roundtables, da-da-da-da-da. And then once they're convinced that because these 4 colleges could do it, they liked it, the teachers enjoyed the teaching even more, the students liked it, everybody, is a win-win-win. Why not make it available to all of them? And at the same time, they offer to have a training center to first bring all the teachers to a certain level to teach this new curriculum. Yeah. So that was our theory, is that you go from a certain critical mass of colleges to the Board of Studies and then back down. Okay, so that's the general idea. Yeah. Before we started changing the curriculum, one very smart teacher and an architect, I don't know if you all know him, his name is Ashoka Fellow. Philippe knows him, remarkable man. He has been pondering this issue of curriculum change in architecture for a long while. And he told us very early on that if you create a new curriculum where the student learns about the Taj Mahal's appearance and the romance of the Taj Mahal and how it was designed to see the moon from a certain angle for his wife, da-da-da-da. And then in another class, 2 years later, you talk about how the white color of a building, reflects sunlight. And then another 1 semester later, you talk about marble and its thermal mass. You have really just done a horrible job. You've really betrayed the child, actually. At that same moment, you need to talk about the whole topic as one whole. The history of it, the technology of it, the design of it, all needs to be spoken of in this one wholesome sense, because that's what makes sense to students. So they said that instead of just focusing on, some classes focus on structure, some classes focus on how the people move, the flow in that space, and some classes talk about sustainability. You try to give equal importance to these streams in the curriculum. Don't make environment a final check. Hey, now I'll go through a checklist and see if it's green. You talk about all these aspects together. That's one thing. The second thing is we made sure that our changes are invisible. Now let me take a minute to talk about this. This is a bit of a contentious issue. Some of the college professors said we should really be announcing that from now on our curriculum is different. This is a new green curriculum that we're going to teach. Some other professors said the moment you say this, there are immediate questions as to, is this legitimate? Is this allowed by the university? Yeah. In fact, now apparently students in India are so neoliberal. They're like, listen, I paid money for this kind of an education. Why are you suddenly changing this education on me? There's like a sense of entitlement, like I bought a service from you. Now serve me, That's how we've become now. So what we realized is that if we can make the change so invisible, and what does it mean really, invisible change? Let me try and convey this to you through an anecdote. Say we asked a student that in which class of your 5 years did you figure out your aesthetic, your approach towards the design? Is there any one teacher who influenced you? Most likely they will say it was a very, very gradual, multidisciplinary, complex process where my architectural aesthetic was formed. It wasn't just one class. But on the other hand, if you ask them, where did you become environmentally sensitive? Who is this? When did that spark get lit? They will immediately pinpoint one star teacher. Now, the problem with star teachers is that when they leave, everything goes with them. And secondly, it still remains one part of the whole approach towards architecture. So we realized that we need to put the environmental subject into all the streams. We also wanted to make sure that the taught subjects and the design studio are in relation with each other. I don't know how it is here in Freiburg, but if you sometimes have semesters where you're teaching a certain kind of material in the materials class, you're talking about a different service in the building services. In history, you're learning about another period, and their design studio is, design a museum in Spain, like no connection at all. It's just a bunch of, eggs in like a crate. That's it. No, yeah. So we realized that has to go. We also realized that the engineering and architecture students are brought up in an atmosphere where they view each other as adversaries. You grow up being, suspicious of each other almost. Oh, these are the numbers people. They're not creative. And those people are like, oh, these are all pretentious artists. And they all grow up and get into engineering firms where they don't really get along. And I know this because my sister is an architect. My ex-girlfriend is an architect. They've always said that they don't really get along with engineers. Engineers don't respect them, like you were saying earlier. Okay, and finally, we want to make the education very learning-centric rather than teaching-centric. Sometimes it means doing less teaching, actually. You can allow the building, the environment, storytelling to do the teaching, rather than you doing it through, chalkboard and the chalk. Okay, so we realized that we want to do this kind of change. Okay, the program physically was quite spread out earlier when we had much more funding, and then there was this condensing of the funding. And now we are mainly working in Mumbai, Pune, and Bangalore, these two cities. These other ones we hope to restart, and we are in the process of looking for funds for this right now, actually in Geneva and other places. Yes, so now what do we really do? The process starts with doing a 5-day rigorous technical training workshop for all teachers, not just some teachers, but we try to bring the capacity of the history teacher, the theory teacher, and the technical teachers to a certain standard. Because if we want the history teacher also to talk about Le Corbusier's influence on climate, they need to know a little bit about how concrete, for example, works differently than other materials, for instance. So you might say, why are you teaching history teachers about building physics? But we actually want to do this. Yeah, and they all have studied it, actually. It's not like they never studied it. It's just that they've become so specialized that they've forgotten all these other things. So first, we do a very rigorous technical workshop. As you can see, it goes into building physics, it goes into solar geometry. Actually, it goes into cooling systems as well. How do cooling systems work? Yeah. And then what we do is we start our curriculum change program. So we start what's called an uptake workshop. It's 5 days long. Then at the end, on the last day, we play a game to design a new lesson plan for the semester. There are lots of post-its and teachers coming up with crazy ideas. Hey, maybe we can do a site visit to this, neighboring building, and we can show how bad the building is rather than talking only about how good the buildings are. Da, 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 da. After they create the lesson plan, and so you can already see we're not imposing anything. We're saying you now decide how you want to change your curriculum. We just are there to maybe nudge them and set the bar a little higher, Then we start a series of bi-weekly calls with them once the semester starts. So we offer them a 2-hour call every 2 weeks where they can talk about the challenges of the last 2 weeks and what do you need for the next 2 weeks. So we go through this, what you might call hand-holding process. It concludes by our team members going into the jury at the end of the year. We ask if we can be observers to see if this semester that got this revised kind of pedagogy, is it translating into the actual design? Yeah. And once we have a successful, this takes sometimes, actually we should draw an arrow. This takes a few, sometimes years to get here, yeah, to see a change. Then once we have this college as an ambassador that really believes in this, we look to organize roundtables with the Board of Studies, where they do the talking. The students actually come up. We are almost like in the background. Yeah, that's the general theory of change. Yes, so I'll just quickly take you through what all we build in terms of pedagogy support. So first is everything that we produce is all in the public domain because we are grant funded. So there's no reason to keep anything, within the walls of, private property, intellectual property. Sorry. Yeah. So all of the training videos, whatever softwares we built, manuals, it's all available on this platform, fairconditioning.org. Then what we've done is, over the last 7 years, we've done so many workshops. I think we've done close to 50 workshops now. In each workshop, we have a session where teachers say, hey, I try this activity to sensitize my students to the problems of the soil, for example. So there's this one teacher who actually makes all the students grow small potato plants. It's a cool activity they've done. And the students start getting sensitized to issues of soil content, moisture, the environmental problem. They're like, hey, this is a cool subject or a cool activity to include in green roof design, maybe. So we keep absorbing like sponges. We have no orientation, exactly. You can put shading, tinted windows. Yeah, of course, then you can turn the AC on as well. Yeah.
What was wrong with the cookies?
Sorry?
What was
No, nothing wrong. It's just that cookies are not a part of our culture so much in the southern India. So this is in southern India. Yeah, this is in Bangalore. Cookies are, you hungry? Okay. Okay, so this is one of the activities, and we have 150 such activities already. And one part of cBalance is always just, coming up with new and, cool ideas to do these kinds of things. Yeah. Yeah. And this is now becoming a dynamic website. We are looking to create a website where teachers from any part of the world actually can upload their experiments in teaching. So it doesn't become a static document, it becomes a live kind of a thing. Okay. We also have in this manual a bunch of physical experiments that you can do to prove how certain physics concepts work. So this is an example. So this is a hairdryer, and this is a wind speed measurement, machine. What do you call it? Sorry?
Sensor.
A sensor, yeah, like a wind flow sensor. Now, without this tube, the speed will be a certain amount, yeah? But the moment you put a tube in between, the speed goes up. This proves that there is something about the laminar, that smooth flow, which makes the air go further. So the throw of the air improves when you have a tube. Now, you might not know the physics, but for an architect student, it's more important for them to create like a memory about this experience. Okay, when I put a tube in between a source of air and where I need to send it, immediately there is a benefit. So this goes hopefully into their bones rather than just staying in the mind as an education, as an equation. Okay, now we're going to do something interesting. This is actually this teaching aid blew our mind, really. And this is, I think, launched, the whole pedagogy manual was launched because of this. Okay, so let me ask you first a question. So please don't look there. I have a question for all the people who know building physics a little bit, or architecture. Say you have air that's blowing in from the right side of the room and to there. Okay, that's the direction of wind in your town. And you make a house in between, yeah? And you want to get the maximum amount of flow through the house, yeah? What would you do? Would you have two windows on either side of the same size? Would you have a small window on the side facing the wind and a big window on the other side? Or would you reverse it? Would you have the big window facing towards the wind and the small on the other side? To get good cross ventilation, what would you do? Yes.
I would put a small one on the wind side and the big one on the outside, on the other side.
Okay. Does everybody agree with him? Convinced? Completely convinced? No? Right? You are convinced. Okay. So you all are an exception. In most places where we do this, there's usually a 50-50% split. Yeah. That some people, and these are all accomplished teachers, no, I don't mean to disparage them. But they don't have a way to think about this in a manner that is very instinctive, you see. Now, this teaching aid actually puts this matter beyond doubt. So this is a simple teaching aid. It's a plastic bottle with the end cut off. This is a wind measurement instrument. That's the small window. This is the big window. This way, it's 2 meters per second. You turn it, it's 0.9 meters per second. There's no need to argue anymore. Whatever the principle is, this happens. Yeah. And once a student knows this, they never forget this. So it's this kind of pedagogy that we want to try and see, even here in Switzerland. Could this be useful? Something of this kind, for teaching building physics concepts, so on and so forth. Okay. So it started off like this, handcraft kind of stuff. And we realized that, hey, schools could really use this, if we made this more, useful, came up with more ideas. So we came up with this concept of a teaching aid kit. And this is now in development, final development in India right now, where we are creating a whole host of, I think, 18 different aids where you can teach concepts of building physics, passive design, including ventilation, insulation, shading, and also do a little bit of design itself rather than using software. So for example, instead of doing shading device design using equations, here you could have a sliding shading device. And by looking at the ratio of the height of the building to the horizontal shading angle with a sundial and on a rotating sort of plane, you could actually check what kind of shading I need for any time of the year using one teaching aid. Yeah. So these are the kinds of things we are constantly thinking up, building, and it all depends on whether we have funds for it or not. You know, and this really excites us. Okay, these are aids to teach cooling technologies actually. So these are more for passive design concepts. These are actually sustainable cooling technology aids. This is what's called an indirect direct evaporative cooler. It's a air-to-air heat exchanger plus an evaporative cooler. This is a radiant cooling teaching aid, which shows how the stratification of the air happens, what kind of temperatures you can achieve with radiant cooling, so on and so forth. We also went to the drawing board and came up with animations that really think of the student's problem. There's lots of animations online which are very technical and they sometimes are very daunting for architecture students. So and also the voices are always American, you know, they sound alien. So we're like, how can we not have animations that speak in the kind of language that the Indian students will understand? So we spent a lot of time and money to come up with India-specific animations for structure cooling, indirect evaporative cooling, radiant cooling, and solar vapor absorption. We also designed some softwares. Like I said, we upgraded this tool called Smart Energy to add these kinds of cooling systems. Earlier, all the cooling systems in this were regular vapor compression based systems. They never even had this. So we said, okay, we need to be able to create a tool where they can model the same building with different cooling systems. Yeah, and this is where we are. We have been working with 4 universities, architecture and engineering. So that's 8 boards of studies are in our target, basically. We have over these last 7 years, now the number has gone up. It's somewhere close to 40 to 50 colleges. We've been training teachers. And we are here basically now because the story is sort of, you know, coming full circle. Years later, looks like Switzerland is going to have a warming problem going further. We just heard from an architect from ATBA, ATBA in Geneva that by 2035, Switzerland is going to need more energy for air conditioning or cooling than it will need for heating. So a big change is coming. And we thought today we could do some, you know, dialoguing towards the latter part of today's talk. What do we think the problem is in Switzerland? Describe the problem a little bit better and come up with some ways in which we can take some real steps towards some system change over here. Curriculum change may or may not be part of it, you know, so that we want to leave this open. We don't want to prescribe any solutions, but we'd like to talk about that. And yeah, just one final thing. We are trying to also address the professional ecosystem in India. We're trying to see what kind of architecture design can we do without even telling the client. Why do we have to get approval for every, you know, building physics related feature that we put in that has to get approval of the client? And yeah, so this is what we mean by non-negotiable versus value addition. Yeah, and yeah, so maybe towards the latter half of today, we could talk about this problem statement. Yeah, so this is a problem statement we could talk about, and maybe I'll pause now. And there is a part of today's talk which is more about actual solutions, just to give some ideas of cooling that we are trying out in India. And but before that, maybe we pause. Okay. Canton, sorry, pre-move, right.
This was a conference yesterday, the same one.
Right.
In Geneva.
So I've been talking a lot. I realize this, maybe very fast. And so it might be nice to just cool down a bit, let things process. And if there are any questions for now, it would be lovely to discuss.
Yeah, so thank you very much for the presentation. I really enjoyed the idea behind the project. I was just wondering though, you are talking about environmental issues which are really pressing. They are at outdoor. globally. But in the same time, you are aiming to work with architecture students. And we know, I don't know much about India, but I guess the architecture market, architecture job market works the same everywhere in the world. And for an architecture student to be relevant and competitive in the job market, it takes several years, sometimes even decades.
Right.
So for these students that you are training now, to be able to design their own buildings, to make decisions about the buildings they are designing, it will be a long term.
Yes.
So I was wondering, first, have you taken this into consideration? And second, maybe are you planning on providing training or consulting for architects which are
Practicing.
currently practicing and designing in India? Yeah, thank you.
Yes, that's a very relevant question. This thing of where to focus your energies on the long term, which if we don't solve the problem for the short term, we will not have a long term, right? So we do need to stop the bleeding at multiple places, and we realize that strategically per euro of funding, we realize that working at colleges is much more efficient, because once you change the curriculum, whatever goes through that new curriculum, all the students are all in an ideal world transformed. Yeah. So we start there, but the idea is to really at the same time be working at the practicing architects level as well. It's just that it's been a challenge in India, and it's different here. I think here the approach seems to be almost demanding another way of thinking. In India, there is no way to change the system of practicing architecture because we don't have continuing education, for example. There's no system where architects have to study every year X number of hours and prove that they are still relevant. Doesn't exist. Here it does. So how do you go to the, I think, 66,000 registered architecture firms in India? I mean, it'll need us to become the size of like, Nestle or something, of the Nestle of sustainable education. Yeah, and we are not that really. So we've come up with a strategy. There is no strategy that we have come up with for system change in practicing architects. We did, by the way, have funding from Oak, and we tried this going to architecture firm by firm, but it's too slow. So it's a very alive question, I think. Yeah. Do you have some ideas as to how in Switzerland, maybe architecture as a field can be supported? Maybe you have some ideas which we could unpack.
Not at all. I was just wondering.
But thanks for thinking of it at a system level. Yeah, the system thinking approaches. It's very vital. Yes.
There's somebody in the chat
who has a question.
Who asked a question, and we should be able to hear it through the mic.
Okay. Hello. Do you hear me?
Yes.
Yeah. Hello, everybody, and thank you for the talk. Really interesting. So I'm sorry not to be there, but at least thanks to Zoom, we are able to chat. And I was wondering about one reflection you share about there are so many people thinking and teachers thinking that if you just plant trees, you will solve a lot of the problem of these climate issues and this peak wave. And I was wondering, I'm part of those people who think that by planting trees and having a city that is greener, we can already transform a lot of the problem of this problem of having hotter climate. But if I understood well, you mentioned that making action on the building itself may be way more relevant. And yes. I have this question about at which scale should we act, and I would like to hear a little bit more about this thinking that planting trees would be a good solution, and maybe you are not convinced. And yes, I would like to hear a little bit more about that.
Maybe there was a misunderstanding between offsetting and shading.
Yes. Okay, so thanks for that. By no means I'm saying that planting trees is not effective.
No, I understood that, but I mean, yeah.
So, but in terms of, if you say efficiency of effort, it's kind of like this, you know, getting overheated. It's because of the urban heat island effect. There's so many other issues about global emissions, so on and so forth. So what we're saying is we need to not just press the brake. So trees are like a brake on the system. That's important, but we need to take the leg off the accelerator as well. Right, so we're not really taking the leg off the problem. We're still pressing hard. Let's build these buildings with AC, and then we'll press the brake. Yeah. And that is, I mean, too much friction, basically. So we need to take the leg off the pedal. And another thing is, when I ask most teachers, how many trees are required to offset 1 ton of carbon emissions? This immediately changes the view on how trees were never designed, by the way. I mean, nature did not come up with trees to solve the climate crisis. They were designed for many other things, for birds, for water, for shade, Now suddenly like, hey, you who are not meant to take care of my climate problem, I need you to take care of my climate problem. So we realized that in India, a tree, you need to plant about 8 typical native Indian trees per ton of carbon emissions. So 1 air conditioner, when we do a calculation in its lifetime, 1 ton of air conditioning, we realize requires about 50 to 60 trees to be planted. And if a college campus in India has close to about 100 tons of air conditioning, that's 100 into 60, that's 6,000 trees. And no Indian campus has that much space. So it's also physically impossible to solve the problem at the downstream end, actually.
Yeah.
Does that?
Yes. So you mean that adding trees doesn't solve the problem, but you should better to preserve what exists already, and maybe think not to build in place where trees are already there. In that sense, you could see the problem in that sense, to preserve trees rather than to add tree to solve the problem.
Right, exactly. Because if less energy is consumed by the building, there's less coal mining, and coal mining destroys many more trees than just at the end of it. So the idea would be to avoid energy consumption, excessive energy consumption in these buildings as well. Yeah. Well, thanks for asking that question. Yes.
Thank you for the great speech. I really enjoyed it, and I love very much your way of integrating the problem in the teaching. I think this is a very convincing approach for our future problems. And so I wondered about 2 things. As an architect, one thing is, what is the result in terms of architecture of your way of teaching? Is there something visible? I mean, is there another style of architecture than Zaha Hadid, or that becomes
the new norm,
or a new way of thinking? So, and the other thing is cooling is one aspect of this. But there is also about building materials, new way of living, and I think you creative approach. So not saying I have the cooling problem and I teach this, but the cooling problem is integrated in a whole way of thinking that is very intelligent. So do you think you could extend this program to other matters? And
water as well, for example, water is another crisis. Thank you for this question. We think of cooling as like this, the tiger of the ecosystem. So we often say that to measure the health of an ecosystem, check, how the tigers are doing, because if the tigers are doing well, lots of other things have to go really well for the tiger to eat. Cooling, if you solve the cooling problem, it requires you to go to materials. It requires you to go to the local, possibilities. It requires you to go to vegetation. It requires you to go into water conservation, because if you conserve water, you can use it for adiabatic cooling. So we realized that if we use this very alive topic, this very immediate threat of cooling, we can use it if we have vision to examine, evaluate, and question many other paradigms as well. So we do get into this. Of course, materials are a big part of what we talk about, so on and so forth. So maybe that's what we should do now, is to look at some of the kind of pedagogy around sustainable cooling and passive design that we do as part of the pedagogy. Yeah. So yes, one final thing I'll say, in the last few years, there has been a criticism of this efficiency approach, like not questioning how much we are building, not questioning per capita how much space we are using, but just doing very object-oriented, design. And there is now a criticism of this. And you might say that the approach needs to become more of a sufficiency approach rather than a pure efficiency approach. Yeah, and I think that is something that we need to figure out how in fair conditioning we are going to integrate sufficiency-related discourses. But that goes at the heart of your identity, actually, almost. Right. Yeah. So some people think of idea of limits, and they're like, run. You cannot question, what I am entitled to. If I am rich enough, I should be able to build the house that I want. I'll do it efficiently, but don't tell me that I can't build a big house. This goes to a very core area of our identity. So we really have to figure out a way to in a way, put these subversive ideas in the curriculum as well. But we want to for sure. Yeah. So it's too late to not try, seriously, it's too late. Okay, so what I would do is we can go to the second part of the talk, which is more about some exciting cooling ideas. Okay, so passive design, we'll briefly take you through some hopefully catalytic ideas about cooling. Some of this might be repetition, so pardon this, please. Okay, so our philosophy of passive design, what we try to convey to teachers is this, that if you do an exercise with students and you ask them to close their eyes and sketch out in their mind a sustainable building in India, usually it'll be a glass building with lots of solar panels all over it. They'll go straight to renewable energy. This has become like the poster child, yeah, the Elvis of this sustainability world is renewable energy. And we realize that, wow, if that is how unimaginative our discourse around sustainable building design is, we really are failing them. So we realize first thing is take the leg off the accelerator. Yeah, let's just stay with that image. Reducing the demand as much as possible. Then you use passive cooling, and then you look at active cooling systems, which are very efficient, hopefully don't use F-gases, and then the remaining load you put on renewable. You don't just build a concrete box with glass facade in the middle of Delhi. Yeah. So literally making an oven. Actually, one friend of ours came up with a great image. Would you ever build an oven and put a refrigerator inside it? That's what a glass building with an AC is. Right? So how do we avoid this whole refrigerator inside an oven? And that's what we talk about. So now pardon me again if you differ with this classification of passive strategies. We read many books, and every book we read classified it differently. So we said, okay, stop it. We'll always argue about this. The point is we need to talk about these kinds of cooling methods. Yeah, some of them are more about the actual design, some about the envelope, and some about moving air around and using free cooling, if you might say. Yeah. Okay, so let's start with some of the design strategies that we talk about. First is, of course, form and orientation, orienting it appropriately. Now, these are all well-known theories, but what we were looking for is convincing modern, manifestations of these classic theories. So we came across a very amazing Indo-Swiss program called the BEAT program, and they, in 2017, they released this new theory of how these principles of orientation, etc., ventilation apply to modern high-rise buildings. Because what works for an individual house is different from a high-rise building. So very quickly, let me show you what this is, okay? So this is for hot and dry climates in India. There are three kinds of typical towers, as they're called, that are built. This is what's called a, you might say, this is called a tower. This is a linear loaded corridor, right? And this is a double loaded, so this is almost like wrapped around like this, yeah? So this one is more square, this is more rectangular. Now, this is a building that is facing, the north side is facing the sun, and here, yeah, it's basically north-south oriented, this building, yeah? The long facade is facing the north or the south. Now, what I would like you to focus on is these numbers. I don't know if they're very clear, but this is the radiation exposure per meter square of surface area. In the tower case, it's 178 on average. In the linear case, it's 147. And for double loaded corridor linear, it's 128. Now, these numbers are not so important in themselves. What is important is when I switch this building to make it like this, make the east-west facing the sun, yeah? What happens to the exposure? And you will see the numbers go up quite a bit from these values to the case of the east-west exposure. So, if you remember the previous number, 147 becomes 219, 128 becomes 187. Same building, different orientation, the heating load increases dramatically. And sometimes students and teachers respond to a lot of this because they're like, okay, theoretically we know all this, but has this been proven? So this is actually a study that did modeling and actual calibration of the model with real world measurements of heat load and so on and so forth. So this is one kind of cooling passive design strategy that we talked about, form and orientation. Another one is the height of the buildings actually. We have learned now from this resource that the most suitable height for buildings in India, for cities, to maximize harvesting of sunlight, harvesting of rainwater, and also doing your own waste management in a relatively self-sufficient way, is about 3 to 4 stories high would be the ideal height for buildings for India. But what is being built is mainly this. This kind of stuff has the most solar exposure. This also has a very high solar exposure, single story, because the roof is being baked under the sun. For example, 2 or 3 story buildings do a lot of mutual shading, they have the least amount of exposure, so on and so forth. This is a study that tries to depict what happens to wind flow when you change the form of the building. So this is, again, I think for Delhi it was done. The same area, built up area is the same. And this diagram here shows, red means, by the way, good wind flow. Blue means dead zones. And you can see that the thinner the plane of the floor, yeah, the thinner, the better the air movement. If you have more of a square thingy, you have more short circuiting and more dead zones created of ventilation. So that's another important thing to keep in mind. Here are some zoning related, ideas, which is if you have a certain kind of building shape, where would you keep the storage areas? Where would you keep the bedroom? Where would you keep the kitchen? Because you might not need air conditioning in the kitchen or cooling in the kitchen. So make sure that is more on the outside. You can protect the bedroom and those kind of things. So these are some of the ideas we talk about. Third one is the size of windows. This is a big difference. You can imagine here, your idea would be to try and maximize the solar intake because you are very, dominated by winters, your climate. Ours is a very summer oriented, like a heat oriented situation. So we are always trying to make sure that our window wall ratio, WWR, is about 40%. This is the new norm in Indian buildings now, is to not have more than 40% glazing in residential buildings. Yeah. If you do have glazing, make sure it's properly shaded. This is one strategy we talked about. This is actually, this is a very well-known iconic building in Mumbai. It's by Charles Correa. This is the concept of deep set balconies providing shading to each other. So that one floor provides shading to the floor below. This is the concept of making sure that if you have glazing, if you have glass, blocking the radiation on the outside is more important than the inside. So imagine if this was, I mean, luckily this is an inside wall, inside glass, but if this building, this wall was facing the sun, this would actually be a failure because you already heated the glass. And once the glass is hot, then it's somehow going to come in. Where is it going to go? So this really is a failure. What you would do is you will shade the outside. Yeah, makes sense, right? So these are some of the ideas that we talk about. Thermal mass, very important to have thick walls where you can, to make sure that you dampen the rise of temperature between the outside and the inside. Cavity walls, these are all well-known things. I'm not going to get into this. Low conductivity materials. And this is one sort of amalgamation of all ideas on the bioclimatic chart. What are all the passive design strategies that you could use to bring yourself into the thermal comfort zone? By the way, this itself, the whole theory of thermal comfort is being rewritten in India right now. Because after years and years of like a colonial method of defining thermal comfort, America defines it for the whole world. Now there are adaptive models of thermal comfort that have been approved for use in India, where you realize that as you become warmer in summer, we can take warmer temperatures. Even 28, by the way, they have proven now in Indian well-ventilated buildings, 28 degrees is cool enough in a double-blinded study. When people don't know the temperature, they say even 28 is sufficient. Yeah. So ventilation ideas, I think this is quite common over here, so I might not go into all of this. Ideas of what to avoid in terms of short-circuiting of cross-ventilation. You want to try and take it from below and pull it up, or ideally these kinds of things rather than short-circuiting, right? So these are some of the ideas we talk about, do's and don'ts to improve the mixing of air. Yes, this is a fun thing. Has anybody here traveled to India or any hot country where you had ceiling fans? Okay, so you'll know what I'm talking about. This is a typical bedroom, imagine, yeah? Where is the warmest air in this house? In a house like this, where would the warm air, if you're going to sleep now, it's 10 o'clock, 11 o'clock, whatever, and you want to feel cool, so you turn the fan on, yeah? But tell me, where would all the warm air in this house be? It would be at the top, yeah, right? Okay. So now what does a ceiling fan do? You turn the ceiling fan on, right? So all this warm air, yeah, you are now going to push it all across the room, right? You're going to pressurize the whole room with warm air. And this shows you how a lot of knowledge about how heat works has been lost. And I experienced this myself. In Mumbai in the summers, the fan is going, it's sounding like a helicopter is about to take off, really. It's going at crazy speed and I'm not feeling anything. Yeah, I'm still sweating under that fan. And the reason for this is because even if you open the windows, the outside air can't come in because you pressurize the room with warm air, basically. So even though it's comfortable outside, you're not able to bring that air in. And apparently, till a few years ago, lots of small cities in India, in smaller towns in the interiors, used to have instead, would have a exhaust fan in the wall. And what you do is you suck the air in rather than you pressurize the air through positive pressure. So you create negative pressure to pull cool air in from the outside rather than try to force the air out with pressure. Yeah. So this used to work and now it doesn't happen anymore. So this is a great situation for air conditioning companies. A simple situation that you could resolve through low technology. Now you have a compressor to do this job. Yeah. Of course, this requires the outside air to be cool, but in a lot of Indian cities, it's quite cool in the night. and all we need to do is bring in that air in. Yeah, nighttime, nocturnal ventilation, and so on and so forth. Okay, I'll take you through a couple other interesting ideas that might be useful to contemplate. So this is what we call, geothermal cooling. It's not technically geothermal, I think, but the idea is basically you take the air in and pass it through a part of the ground that is always at around 20 degrees. And the air cools as it comes in. And what starts off as 35-degree air becomes maybe 25, 26 degrees. And it still might not be good enough for air conditioning purposes, but at least you've gotten a big part of it done by simple heat exchange with the ground. All it needs is foresight and for you to do it before the construction begins. So there are now quite a few big campuses. In fact, TERI, this very well-known environmental NGO, the entire campus has earth air tunnels below it, to get this free cooling benefit. Another idea which is slowly coming back into practice, hopefully not fashion, into practice, is the wind tower or the wind catcher. And I heard recently this BedZ project in Europe is trying to make it more versatile, useful, and implementable. So basically the idea is you orient it in a way which allows for most hours of the year to scoop the cool air and use it in the house or in the building. This is the courtyard effect. I don't know if this is well known here, but traditional Indian homes usually had a courtyard in between. So you had the houses here, and in between was like a small little garden and a pond, etc. And the logic was this, that if it's dry enough, relatively dry, that there is evaporated cool air over here, in the center. And if you have a mix of shade and sun, then what happens is wind currents can develop. Yeah. So you actually make sure that it is not so wide that everything just gets baked, and it's not so narrow that there's no warm air at all. So you have to have some sort of a pressure difference, and you create this courtyard cooling effect. And as the air rises here, it pulls in cool air from the outside. Yeah. So it creates like this, kind of like what you showed me. The air from the bottom is going up in this building that we just saw. I forget the name now. The good idea next door. Right, exactly, right. Yeah. Yes. Now this is, I guess, a very sophisticated way to do evaporative cooling without adding humidity to a building. Okay, so let me explain this thing. By the way, anybody has heard of this term? Passive ground draft cooling? Have you ever encountered this? Okay, so imagine this is the building that you want to cool, and here is a tower that you construct filled with lots of bricks, high thermal mass bricks. What you do is you provide, along with it, you provide a sprinkling system. Yeah, you sprinkle water, and through the whole night, say the building is occupied only in the daytime. So in the night, you sprinkle water on the bricks, and it's just trickling, trickling, trickling. And then what you do is you allow for air, relatively cool air in the night, to come in, and you pull it through the entire tower. But you don't use that air. What you're trying to do is you're trying to keep this entire thermal mass. It's like thermal storage. You're trying to create a cool block of thermal mass through the whole night. And then in the daytime, what you do is you shut the exit and you open the inlet, and now the warmer air in the daytime gets cooled through heat exchange, but not through humidity addition. So this is a good way to do evaporative cooling in the night, create thermal storage, and use the non-humidified air, not dehumidified, non-humidified cool air for air conditioning purposes in the building. And to add more sort of boost to the flow, you can have a solar chimney. This part can be, facing the hot part of the day of the building, and this can be black even. And so you create a pull effect here and almost a push effect over here. So this is an actual example of a very well-known building in India. It's called the Indian Green Building Center by CII IGBC. And it's in Hyderabad, a very, very hot city. And these towers work really well. I think each one of these provides about 12 tons of cooling. Something. So this is 12 plus 12, 24 tons of cooling. This is providing.
What's the unit?
Tons of cooling.
Tons.
Tons. Tons of refrigeration. TR.
Okay.
Basically, it's equivalent to 3.5 kilowatts of cooling.
Yeah, that same one. John likes to. He loves the cake. Okay.
Okay.
White chocolate stuff. I'm talking about.
Okay. So I was causing heated debate. Okay, so this is just a diagrammatic representation of what I was saying. In the night, what we do is, by the way, this is the tower. These are the bricks. You sprinkle water, you keep cooling it, and in the night, you just keep discharging that air. Yeah, you're just doing this. In the daytime, you close this, you open this, and then the warm air gets cooled and gets used in the building. Yeah, pretty simple. Okay, this is an example of a passive downdraft system being used in an auditorium in one of the hottest parts of India. They have these small little ducts coming out with the passive downdraft cooling, and there's no air conditioning, and it works in a place that has 45 degrees very regularly. It's in Gujarat. Yeah, that's some of the passive design technologies. And what I finally wanted to do was talk about one active cooling technology, which is called structure cooling. We briefly touched upon it. I think it is the most useful manifestation of an old technique. I mean, these kinds of techniques of cooling a structure have existed for a long while, but very few buildings have been able to do it in a very modern context. So I just wanted to add one final spark to the ideas, and then we can maybe do questions and yeah. Okay, one quick anecdote. There's a person who is 87 years old. He worked with Carrier for 30 years. Yeah, this person was a very well-known air conditioning consultant in Mumbai. During a visit to the historical part of India in New Delhi, the tour guide, yeah, not a building physics expert, was talking about how a certain ancient monument was kept cool using water in the floor and all of this. And this person's wife asked him, saying this, oh, so this is what your cooling business does. Now I understand the principles of how Carrier and all these air conditioners do cooling. And he had an absolute thunderbolt moment, and he was like, no, that is not what we do at all. And he had a moment of such awakening. He quit from Carrier. And since then, for the last 30 years, he has been unlearning air conditioning. He's 87 years old, and still every 2-3 days he'll call me, hey Vivek, I have a new idea I want to discuss. He's still inventing. This guy is an absolute powerhouse, Philippe has met him. Okay, so structure cooling is Mr. Surendra Shah, it's his baby, and he is more than happy to just let all the knowledge go into the world. He doesn't believe in holding on to anything. Yeah, so any further questions you have, please do let us know, and we would love to put you in touch with him. Okay, so why structure cooling? I have 3 questions for you. As people who know a little bit about materials and air and all of this, insulation, do you agree that air is a medium that is designed to block the transfer of heat and not promote heat transfer? Most often, air is used to stop heat transfer, right? In insulation, so on and so forth. So, in general, air is not a very good thermal medium. So, this is one thing we should keep in mind. Now, the second is this question. If you want to empty a tank with the least amount of energy consumption, and I gave you a pump or a drain, which one would you use? A pump or a drain?
Drain.
Drain, right? But what is an AC? An AC is a pump. It works against gravity, right? A drain, if you can drain the heat from a building structure, and the structure is nothing but a tank of heat actually. The sun is baking it the whole day, the heat is there in the walls, and what are we doing? We're allowing the heat to come in, and then I'm pumping it out. Why not just drain it from the structure? That was his big aha moment. Why are we pumping when we could be draining? Yeah. And finally, if you had a choice of a heat transfer process, and I told you that air conditioners are based on a linear linearly proportional temperature difference. That means if the difference between the air and my body is say 10 degrees, to get double the cooling, I have to double the temperature difference. Versus say radiant or structure cooling, where the temperature difference gets multiplied by the 4th power, which means if I double the temperature difference, I get 16 times more cooling. Which one would I use? Of course, I would use radiation. But for some reason, radiation doesn't find any mention in the thermal comfort science, even though technically it is there, by the way. Mean radiant temperature is a big part of thermal comfort, but the air conditioning industry does not talk about it. Yeah. So what we're trying to do is we're trying to bring this very important parameter of the surrounding temperature into play. Okay, so how does this work? Yeah, by the way, the reason why water is a better medium than air is because it is 3,400 times more efficient in absorbing heat than air. Now, most architecture students or teachers would not know why this is the case, but if I ask you a question, if your hand gets burnt because of a flame, yeah, and I give you 2 options, there's a tap of water and a fan. What would you put your hand under? Water, no brainer, right? You don't need to know building physics for this. So why are we constantly throwing volumes and volumes and volumes of cool air when a little bit of cold water could pick up much more heat? Yeah. Okay, so that's why we need to look at what water can do. So the logic of air conditioning is what? Throw cold air on someone, make them feel cool. Structure cooling is completely inverse. You become your own source of cooling, because rather than cooling me, I'm cooling the walls and my body will radiate the heat to the walls. That's the logic of structure cooling, yeah, or even radiant cooling. But structure cooling is even smarter, I think, because it drains it from the structure to begin with. Yeah. So the working principle is all based on lowering the mean radiant temperature, right? In general, air conditioning focuses much more on this, much more on this, much more on this, all cause a lot of environmental damage to make this happen, whereas we could be working much more with radiant temperature. Okay, there's a lot of theory to go into. I don't want to bore all of us with it, but the basic idea is this. If you want to question the dominance of air conditioning, designers are going to have to learn how to keep the mean radiant temperature less than the skin temperature. This is the main thing. If your walls are at 40 degrees and you are at 35, you enter that room, you're going to need to either turn on the switch of the AC or leave the room, right? So we need to drop the wall temperatures below 35. That's the main thing. That's the idea, right? The person's body temperature, okay, I don't know why it's 30, but usually warm-blooded people should be 35. So this is 30, okay, so 30 degrees is much cooler than 21, right? And this person's body is radiating heat to the surface. That's the general idea. Okay, so to test this, Mr. Surendra Shah, 87-year-old guy, comes up with a demonstration project on top of his industrial estate building. So this is a demonstration project. This is a concrete tank with 2 parts to it, left and right. This is cold water. This is warm water. This is the slab. You imagine slab, okay, the word for slab is what? Like a floor or a thick concrete ceiling that's about, say, 1,000 square feet. Yeah. And what they've done is they've embedded inside this plastic polypropylene pipes. And I'll show you some pictures. And this is a radiator plus what's called a heat pipe. So this water, the warm water goes here. And here there is copper tubes which have a refrigerant in them. But the smart thing about a heat pipe is there's no electricity use. It's a completely sealed vacuum. There's a vacuum inside and there is refrigerant in there. Warm water causes it to evaporate. As it evaporates, it cools the water. As it rises, the cool air that the radiator, this fan is throwing on it, yeah, allows the refrigerant to cool down and goes back down. So it's like this passive heat radiation system. And that cool water comes back in and is ready to be circulated again. Very, very simple. You might wonder, like, why is this not happening in as many places as possible? Okay, so this is a schematic of what I just showed. And I'll show you actual pictures of how this has been done in some buildings in India now. So this is a regular concrete ceiling. By the way, this can be done in retrofit mode. You don't need to do this in the beginning. If you've already made the building, it can be added to a building. Yeah, so you put these jointless pipes. Less joints, the better, less chance of leakage, so on and so forth. And even though it's plastic, it does have a very good conductivity because they're relatively thin pipes. So the heat transfer is not really impeded over here. Then you cover it back up with some sort of a plaster and waterproofing you can do, so on and so forth. This is the radiator. This is a small holding tank. The real tank is actually underground. In this case, they're using even the ground cooling to cool the water beyond the radiation. And this is a manifold to isolate those pipes. If one of them has a leakage, you can just take it offline and you can then repair it, so on and so forth. These are real test results. What I want you to focus on here, these are 4 different projects, by the way. This is in the city of Jaipur, Rajasthan, the hottest state in India. Rooftop temperatures are about 52 degrees, 52 to 45. When you turn on the direct structure cooling, as it's called, the temperature goes from 45 below the roof to 28. It really works. This is actual real world data, and it drops your cooling load by a significant amount. Yeah. The other versatile aspect of this is that you can use the same thing for warming. You just run your solar hot water system through the same network of pipes and it creates structural warming rather than structural cooling. These are pictures. This is an auditorium in Mumbai. It's about 7,000 square feet. This was put in after the auditorium was built, many years after, and it has reduced the air conditioning demand by 30%. This is proof that this is useful even in the intermediate floors. So one question often architects ask is, what if we have a high rise? This is because heat is like water. The moment your heat touches the surface of the building, somehow it's going to make its way through all the concrete. So you can drain it out wherever you want, actually. It doesn't have to be done only at the interface of the sun. It can be done in every floor. Yeah, it's just a matter of cost. But this is an example of a building that has done it in every floor. This is what the rooftop sort of looks like. And finally, this is proof that this is really passive. You can't even tell that there is a cooling system actually. It's all in the floors and the ceiling, kind of like a radiant system, but even more embedded into the actual structure. And leads to a pretty cool, minimalist aesthetic if that's what you want to go for. And architects really like this attribute that you can avoid all the ducts and all these things hanging and all of that. Yeah, this is final proof of some energy savings. We have seen that in, okay, not radiant cooled, sorry, structure cooled. Monsoon, post-monsoon, like October, for example, is the hottest and the most uncomfortable month in India, at least Mumbai, is October. There you will need some air conditioning, but then leave with me and the input part of today is over and we can take questions and talk about what you find interesting, things you want to clarify.
Thank you very much.